Okay, in this problem, I would like to perform a transient dynamic analysis on a block that is meshed with solid elements and harmonically loaded at a particular point. Now, this particular problem, I also did it as a separate video with beam elements. And uh, the only advantage, at least the advantage that immediately I see in doing it with solid elements, if you want to see the stress distribution in the part, then doing it with beam elements is not going to be helpful because Catia will not support that. And so that's if you want to see the stresses, then you should be doing it with solid elements. Now, this problem is a linear elastic problem, and in fact, transient dynamics, or some people call it linear dynamics, in general is meant to be for a linear problem, and therefore one has to perform a frequency analysis to find the modes because it's based on modal superposition. Okay, so let me go ahead and the analytical solution for this as a beam problem is given down here. Now, I already showed you that with the beam elements, it matches this thing pretty good. And let's go ahead and do this problem. So we have a 1 by 1 square cross section, which is 20 inches long. So on this vertical plane, I will sketch a why don't I make it a centered squared? So this is going to be 1 inch, and this is also going to be 1 inch. Let's change these, 1 and 1. Exit. And by the way, we are not using any symmetries in problems which involve the eigen frequency or eigenvalue calculation or natural frequency calculation or buckling load. Remember, I suggested to you not to use any planes of symmetry unless you're absolutely sure that you're not making a mistake. So this one, I'm going to go 20 inches long, right there. Good. Now, I can make this out of steel. Let's go ahead and do that. Actually, metal, make it out of steel on that part. And these properties that are taken in the MathCAD worksheet here are exactly what is given to you in the Catia default properties of steel. Therefore, I don't have to make any changes. Those values are actually taken from this. Now, right, so we can go ahead actually and mesh this thing. So we go to generative structure analysis. What happens is that, now remember, you need, in order to do dynamics, linear dynamics or transient dynamics, you have to do a frequency analysis first. But you also need to do static analysis first, because if you don't, then there's no opportunity for you to apply load. So what we're going to do, if I say okay, I'm going to delete this thing. You'll see why in a second. So you can see the mesh. However, I want to apply my transient load at the particular location here, which I cannot just go ahead and take it like here. If I want to apply load here, for example, notice that in Catia you cannot apply load directly to nodes. So what I need to do is to make sure that there is a point that I create where I want to apply the load, and that point is actually becoming part of the node system of the problem, which means that you cannot do it in generative structure analysis with this type of a mesh. So I'm going to delete this. You see why? I'm going to delete this. I don't want that. I still have my part here. Let me create a point up here, which is exactly at the location where I want to apply the load. So let's say that this is going to be x is 0, y is 10, and z is 0.5. So you can see that a location has been created right there. Okay. Now putting the force on this node, on this point, is not going to do you any good because this is a geometric entity, and when you put a force here, it'll take it, but it will not take it into account when it comes to doing the calculation. So what we're going to do is, instead of, we can go first of all to generative structure analysis. There's no problem. Actually, let me not do that. Go to advanced meshing tool. Okay. Yes, static analysis is fine. There's no problem. But then we have to mesh ourselves. So here is the situation with the mesh octtetrahedral mesh. This is the same one that was used when we went to the generative structure analysis. The difference is that there are things you can do here that we had no option of doing it if I went to directly generative structure analysis. For example, I want to say impose point, add a point. So I click on the impose point, add, it says, okay, where is it? Well, it's this point. Let me hide that. Oops. Let me cancel this. Hide this guy so that it's not blocking my view. Good. So impose point, add. This is the point right there. So there will be a node there for sure. You say, okay. In fact, you can look at your mesh. If we go back to the generative structure analysis, let's go back to generative structure analysis. Right there, we can say, show me the mesh. There will be a node right at that location, right there. You see that? There will be a node. This is the same point that I had before. As a matter of fact, you say right click, hide and show, right there. You see that? That became a node, and you can put a force on it, no problem. So let me hide that guy. Very good. Now, all right, first we're going to do static analysis. We want, this is a horrible mesh. I mean, you already see this. So let me go ahead and make it smaller, actually. So maybe 0.5. And show me the mesh. Oh, cancel. Show me the mesh. That's more respectable, okay? And in fact, you can see that your node is right there at one of these locations. Okay, good, good. So let me hide this again. All right, deactivate this mesh. Now, to make this thing simply support at the two ends, we have already done things like this before. In one of the tutorials last week, I did, for example, a pivot here and a virtual part. But initially, I put this thing on a pin this and do the same thing. So I'm not going to use virtual part. So I'm going to do that with a very straightforward, take this, say that it does not move in X, Y, Z direction. But aside from that, this is fine. And then on the other side, it's on a roller, so it can move in the direction Y, but it cannot move in X and Z. Okay, good. Now, we're going to apply load here, 100 pounds downward. So there's a force at that location. Now, because we already took into account that this becomes a node, the force is going to be placed at that node. So we say, okay, as a matter of fact, you can see it. If you say, show me the wireframe, right there, you can see that. Good. Put it back to this. All right. No big deal. If you run this thing, it's going to be nothing exotic. This is going to bend. So let's run it. Let's try to run it. Oh yeah, because I did a manual meshing, I forgot to put properties here, so I have to do that right now. When you do that in generative structure analysis, automatically it puts properties there, but since I did this thing in the advanced meshing tool, I have to go to model manager, 3D property, I have to select this, notice that it picks the material steel, and fine. Now when I run it, it doesn't complain about not having properties. The properties, you can see that this branch was populated right there. See that we didn't have this thing before, right? Good. So nothing exotic here. There's the, static solution. We do need the static solution because this is the load. This load is what we're going to be using later on when we do transient dynamics. Okay, so let's go ahead and deactivate this. Deactivate that. Good. Now we're going to go and extract, insert the frequency case, insert a frequency case, and restraints are going to be from the static one that we already ran. It's going to be the same restraints as the static one. We say OK, and it's going to extract 10 frequencies. Some of them are bending, some of them are axial, some of them are torsional. I'm not going to worry about these things, so let's go ahead and just run it, and we can check out, see who is who once it runs. Good, that's done. So look at the deflection. There we are. Now this, for example, is bending. Yeah, bending as we want it, but you can go to the other one. This one is bending in the other direction, okay, etc. So you know what, we're not gonna pay attention. These are important. Like this one, for example, is bending. So we're gonna say use all 10 of them. If you put your loads so that it doesn't excite those, then it doesn't matter. So we're going to use these default 10 frequencies. Some of them are useful, some of them are not going to come into the picture because the direction that you're applying the load will not actually excite those particular modes. So let's deactivate this. Good. We extracted 10 frequencies. Now we're going to say insert uh, uh, transient dynamics right there. Insert transient dynamic response. Okay, for frequency says, do you have a reference? Yes, we did that. We just did the frequency. We extracted 10 frequencies, and we say okay. Good. Now, the problem is that when we try to apply the load here, see that this load. Uh, uh, if you double click on the load excitation, it says where is the support. Where is the load? The load is whatever we applied in the static case, right there. This. That was, remember, we put a force minus 100 pounds downward on this. And then it says excitation, modulation. But the problem is that I did not do modulation. If you look at the previous video, I went through exactly the same thing, and I told you that, oh, we don't have a modulation now, so we have to create one. So we say, okay, we can't do that here, all right? So let's go ahead and do that. We need an Excel spreadsheet. Please watch the other video with Beam. It's the same story. So let's go ahead and start with a Excel spreadsheet. That's going to be our modulation. Over here, first column is X, or in other words, X-axis. The second column is the Y-axis, and basically they represent this. F naught is already taken care of. It was minus 100. It's sine omega t. Basically, this sine of omega t, we have to plot it as, we have to input it as first column being t, second column being sine of omega t. So here it is. This is first column is in seconds, x in seconds. Second column, no units, just like that. So this is going to be 0 to every 0.01 second, and go all the way to 102, which gives you total time of 1. So we're going to do this calculation over total time of 1, and this is equal to sine of 7 pi times 3.1415. We did exactly these same things when we did it with beam element. 1415, and then times that column times t. We close this. This is the exact same spreadsheet. I could have used that one, but I decided to do it from scratch. Okay, very good. Okay, so file, save as, browse, desktop, April, what do I call this thing? Desktop. April right there. So I'll call it solid modulation, solid element modulation, solid element modulation. Time modulation, obviously. Okay, so I can close this. I go to Catia. First, let's import that. So here is the modulation toolbar. Right there, you can see that. This is white noise, which means constant overall time or overall frequencies. Frequency modulation, time modulation, or time modulation. So we go find it, browse. It was this one that I created. That's my Excel spreadsheet. Good. So now we have in our tree, we have a modulation that was imported. I could have given this thing a meaningful name, but I didn't, unfortunately. That's okay. So you click on the load excitation. For the load, you go to the one that you did for this for the static case. For the modulation, we just created one. We go to the tree and select it from the tree right there. Right there, you see that? I went to modulation tree, selected this. And because I already put a minus 100 down, I don't have to use a scale factor. But if I had put minus 1 down, I would have put 100. If I had put 1 pound, I would have put minus 100 here. But this is a scale factor. That's okay. Now, that's pretty much it. Like, we don't have to run anything. So we put the cursor there, right click, generate 2D display. Next, finished. Remember when I did this thing with my other computer, it crashed, so I had to do in 2 different computers. So I minimize this, and I have to really go and select that. Where is that thing? I have to go and select that. Let me see for a second. Select that node. So where is that node? What is this? Nope. Okay, so see, ordinarily, oh, that's because I probably deactivated this. Let's activate it. Okay. Let me cancel that for a second. Close. Deactivate that. Let me see where my mesh is. My mesh is up here. Because you have to get the node that you want. So activate the mesh. Good. So let's go ahead and get that plot. I have to select my node or my node. So let's do another one. I don't like that. Let me delete this. So right click, generate display to the display. Next, finish. You know what? This is kind of strange because on this computer, I don't get the nodes. I'm sure they're there. It's in the background. If you look in the high hidden zone, I'm not sure why it's hidden. You should try it on your university computer. Hopefully, you won't have that issue. But here, you can actually select nodes. You can see that. Let's hide some of the stuff that we don't want it. Oh, let's check. Ah, there. Okay. So I actually, for some reason, my mesh hides here when I do solid elements. It didn't happen when I did beams, but what I did is I went there and said, show me the mesh. That's why the mesh is now all in the front, okay? So it's this point that I wanted, wait a minute, yeah. Oh, you know what? I actually wanted to put the node at this is the place that I want to monitor thing. I made a mistake. I wanted this point to be at the quarter point. No problem. Close. Okay, good. So let's go back to let me get rid of this. I mean, one makes mistakes like that, but you have to fix it. As simple as that. So if you go to the part body, remember I created several points. Oh, actually, this is the point on the top. Yep. I wanted this point to be actually at the quarter point, so not 10, but 5. Yes. Everything is going to be the same. So go to the analysis. Okay, very good. All right. Let's see where we are. Let me put this thing down. Okay, so let me delete this. Okay, let's try it again. Right click. You may have to run it here. I'm not 100% sure, but let's go ahead and run it. Fine. Okay. So right click, generate 2D display. My mistake was that point that I created and I put the load on it, I put it in the middle. Should have been quarter point. That's why I have to go and do a cleanup basically. So we go here. Now the place that I want to monitor is halfway in the middle. Now if you're having problem finding this thing, what I suggest is you create 2 points. One of them is for monitoring purposes. The other one is for applying the load. So let's say that, somewhere in the middle. You understand what I'm saying? Like I created 1 point because I wanted to apply load there. Create 2 points, one for putting the load, the other one for monitoring. So let's say this one, not one. Node 191. You say OK, and where is the graph? The graph is hiding in the back, right there. Now, the problem is the timing. Okay, so let's go in and fix the timing. I never paid attention to this time. Double click on this thing. I want to go from 0 to 1. That's what I did last time. And let's say in 100 steps. And now, let's close this. Right click. Can we update it? So maybe not. Maybe yes. Let's see now. Ah, there we are. Okay. All right, good. Now, let's see for a second what's going on here. We want, if you put the cursor there, this is a meter, right click, options. Okay, remember the units we have to change here. Right click, options, not the MKS unit, but the units that are used in my problem. Okay, so this is in inches now. Do I want the amplitude? There's two things here. The blue one is displacement in Z, and the green one is displacement in Y, because this is on a roller. It can actually move to the right, so there's two components. Now the things that I want to do is I don't want it in amplitude form. I want it in the real format, real. There we are. So this. And please note that these displacements are very much the same as what I got before. Now, this is the displacement in the horizontal direction, which, it's very small compared to that. That makes sense. However, I want to point out to you that there's an automatic damping here. See that? When you click on the wrench here, it was a 1% damping which was applied. So I say 0. If I want no damping, I say 0. Say OK, because this solution does not involve any damping. And say OK. Now, if I click on this graph that was created, that was based on the damping that we had before, 0.0049, 1%. So I want to see, if I want to sit without damping, no problem. I do another one. Right click, generate 2D display, next, finish. I have to go here and select that node 191. I was lucky. Right there, 191. Add. And we say OK. There is the new graph. And notice that no damping. It's yep. just a second now. This is oh, I have to convert from not this is meters. No, right click. Uh, let's change the units first. Right click, options, not MKS. Yeah, okay, good. And fine. Right click, format, real, right there. And there we are. So